All right, get ready because we are taking a deep dive today into the Competitive Programmer's Handbook.
Absolutely.
It looks like someone's getting ready for a coding competition.
Or just sharpening their algorithmic skills.
That too, just a little brain workout.
Yeah, exactly. It's a great book for that.
So where do we even begin with a handbook like this?
Well, chapter 2, I think, is a great starting point. It dives right into time complexity, which is like the heartbeat of competitive programming.
Okay, so time complexity in the world of competitive programming, every millisecond counts, right?
Absolutely. Imagine you're in a race and your code is up against thousands of others, all vying for that fastest solution.
Oh, I can feel the pressure already.
Yeah, and that's where understanding big O notation becomes so crucial.
Big O notation. Okay, that always sounds a little intimidating. Can you break it down for me? What's the big deal with like O of N and all those cryptic symbols?
Sure, think of it like a speedometer for your code. It tells you how much slower your algorithm gets as the amount of data you're processing, grows larger and larger.
So if my code has a time complexity of O of N, it means the time it takes scales linearly with the input size, like double the data, double the processing time.
Exactly. But if your code has a time complexity of like O of n squared, things can get really messy quickly.
Oh,
Double the data and the processing time quadruples.
oh, wow.
Yeah, you can see how in a competition, choosing an algorithm with a better big O notation can be a real game changer.
It's the difference between winning and losing.
Absolutely.
The handbook uses the maximum Soubre sum problem to really illustrate this. It shows how a brute force approach with its O of n squared complexity, well, it can really crawl to a snail's pace.
Yeah.
Compared to Kadane's algorithm, which zips through the problem with that elegant O of n efficiency.
It's a beautiful example of how a clever algorithm can make all the difference.
So the handbook is really guiding us on how to analyze code snippets and determine their time complexity, which I guess is like learning to read the speed limits of our algorithms.
That's a great way to put it.
All right, so chapter 3 takes us into the world of sorting. And, I used to think sorting was just about arranging things alphabetically.
Right.
Boy, was I wrong.
Sorting is so much more than that. It's really the foundation for countless other algorithms. Whether you're searching, merging data, or finding patterns, having your data sorted can unlock some incredible efficiencies.
I'm starting to see that.
It's a fundamental building block.
The handbook dives into merge sort, which is this fascinating recursive algorithm that just keeps breaking the problem down into smaller chunks until everything's sorted.
Yeah, merge sort is a great example of a divide and conquer strategy. It's like neatly organizing a messy room, You start by sorting piles of clothes, then you sort items within each pile and so on, until you have a perfectly organized space.
I like that, a very visual analogy.
Yeah, and the best part is a merge sort guarantees a time complexity of O of n log n, which is considered optimal for comparison-based sorting algorithms.
So we can't really do any better than that.
Well, the handbook even explains this concept of a lower bound, proving that no comparison-based sorting algorithm can do better than O of n log n. It's like a speed limit set by the laws of computer science.
We have to respect the laws.
Exactly.
But let's not forget C++ built-in sort function.
Oh, yeah, that's a good one.
That thing is a powerhouse, already optimized for speed, and often your go-to choice in competitive programming.
Absolutely. It's a great tool to have in your arsenal.
It's like having a super fast sorting machine at your fingertips.
Exactly. And the beauty is you don't even have to know how it works under the hood. You just use it.
But the handbook also explores sorting by multiple criteria, like sorting points on a map, first by their x-coordinate and then by their q-coordinate.
Right.
And it covers user-defined sorting, where you can create custom comparisons for your own data types. Imagine sorting a list of superheroes not by their names, but by their powers or weaknesses. The possibilities are endless.
Exactly. It's all about flexibility and tailoring the sorting to your specific needs.
I'm already starting to see the power of sorting beyond just alphabetical order.
It's a foundational concept that's going to come up again and again.
Speaking of efficiency, Chapter 4 introduces us to the magic of binary search.
Ah, yes, binary search, a classic.
And it's more than just finding a number in a sorted list, right? It's about finding things fast.
Absolutely. Think of it like searching for a word in a dictionary. You don't start at page 1 and flip through every single page, do you?
No, I'd never find anything.
You open the dictionary somewhere in the middle and see if the word you're looking for is before or after that page, and you keep narrowing down your search. That's binary search in action.
That's a perfect analogy. And the amazing thing about binary search is that it achieves this logarithmic time complexity O of log n, which just blows linear search out of the water, especially when you're dealing with large data sets.
Oh, absolutely. Imagine searching for a specific book in a library with a million books.
Oh, that sounds like a nightmare.
A linear search might take you a million steps in the worst case, but with binary search, you could pinpoint that book in just about 20 steps.
Wow, that's incredible. The handbook dives into helpful C++ functions like lower bound, upper bound, and equal range, which are like specialized binary search tools for finding specific elements or ranges within a sorted set of data.
Yeah, these functions are incredibly useful for problems where you need to find the first, last, or a range of elements that meet certain criteria.
I can see how those would come in handy.
Absolutely.
Okay, now Chapter 7 is where things get a bit more challenging, dynamic programming.
Dynamic programming, yeah, it's a powerful technique, but it can definitely take some time to wrap your head around.
It's always seemed a bit mysterious to me. Is it really that hard to grasp?
Well, the key is to understand that you're breaking down a big problem into smaller, overlapping subproblems, and then you're storing the solutions to those subproblems to avoid doing redundant calculations.
So it's about being smart and not repeating work we've already done.
Exactly.
The handbook uses the coin problem as an example. You need to find the fewest coins to make a specific amount of money, like something we face every day when we're making change. But to solve it efficiently, well, that requires a bit of dynamic programming magic.
It's a classic example, and it really illustrates the power of dynamic programming.
Another classic example is the knapsack problem, where you have a knapsack with a limited weight capacity, and you need to choose items with maximum value to put in it. It's like packing for a trip, but with algorithms.
Packing for a trip with constraints.
Exactly.
And you want to maximize the value of what you're taking with you.
And then there's the longest increasing subsequence problem, which sounds simple, but it can be surprisingly tricky to solve efficiently.
Oh yeah, it's a great example of how a problem that sounds straightforward can have hidden depths.
So dynamic programming is really about recognizing those overlapping subproblems and then using memorization, which is like creating a lookup table of solutions so you don't have to keep recomputing them.
That's the essence of it, yeah. You're trading a little bit of space to store the solutions for a lot of time saved in computation.
Clever. Chapter 8 introduces amortized analysis. And honestly, that sounds more like something from the financial world than computer science.
It does sound a bit like financial jargon, but it's a really useful concept in algorithm analysis. It focuses on the average cost of a series of operations, even if some individual operations might be more expensive.
So it's not always about the worst-case scenario, but rather the overall performance over time.
Exactly. It's like saying, even if your car needs an expensive repair once in a while, as long as it runs smoothly most of the time, the overall cost of ownership is still manageable.
I like that analogy. So with amortized analysis, we're taking a long-term view of efficiency.
That's right. And the two-pointers method, also covered in Chapter 8, is another great tool for analyzing algorithms that work with arrays and ranges.
2 pointers. That sounds surprisingly simple.
The simplicity is part of its elegance. Imagine you have 2 pointers, like your index fingers, pointing at different elements in an array. And you move those pointers strategically based on certain conditions.
It's like a carefully choreographed dance of pointers, moving through the data to find the solution.
That's a great way to visualize it. The handbook shows how this technique can be applied to problems like finding pairs of elements that sum to a specific target value, or finding the nearest smaller elements in an array.
It's fascinating how such a simple concept can be so versatile.
Absolutely. And then we have the sliding window minimum problem, which takes this idea to another level.
Okay, tell me more about that one.
Imagine you have a window that slides over an array, and you need to find the minimum value within that window at each step.
So it's like having a spotlight that moves along a line of data, always highlighting the smallest value in its beam.
Precisely. And this technique has applications in all sorts of fields, from signal processing to image processing, anywhere where you need to analyze data streams.
Okay, I'm starting to see how these seemingly simple techniques can have such a wide range of applications.
That's one of the most exciting things about algorithms. They're like building blocks that you can use to create incredibly powerful and sophisticated solutions.
Chapter 9 jumps into range queries, which are all about efficiently finding information within specific portions of an array.
Range queries are essential when you have a massive data set and you need to quickly find things like the minimum, maximum, or sum of values within a certain range.
It's like having a super-powered search engine for your data.
Exactly. The handbook starts with static array queries, which work great when your data doesn't change. You can pre-calculate the answers for speed.
It's like having a cheat sheet with all the answers ready to go.
Precisely. But what if your data can change?
Good point. That's where things get more complex.
That's where we need more dynamic data structures, and the handbook introduces two powerful ones: the binary index tree and the segment tree.
Oh, I remember those. They seem pretty mind-bending at first glance.
They are clever structures, but the handbook does a great job of explaining how they work, using clear diagrams and examples, and it even ties in the technique of bit representation, which can sometimes lead to surprisingly efficient solutions.
Okay, my brain is starting to feel a bit full, but in a good way. This is a lot to absorb, but it's fascinating to see how these algorithms and data structures work.
We've definitely covered a lot of ground, and this is just the beginning. There's so much more to explore in the Competitive Programmer's Handbook. We'll dive into more advanced techniques in the next part of our deep dive.
I'm ready for the challenge. Let's do it.
Excellent. Get ready for more algorithmic adventures. It's like we've unlocked the first few levels of a coding game.
Okay, I like where this is going.
And now we're ready to tackle the boss levels.
Bring on the challenge.
The Competitive Programmer's Handbook is full of strategies for those really challenging problems that can make you stand out in a competition.
All right, so what's next on our algorithmic adventure?
Let's jump to Chapter 5, where the book introduces a technique that might surprise you: complete search.
Complete search. Isn't that just brute forcing, trying every possible solution? I thought we were all about efficiency here.
Well, it's true that complete search involves systematically exploring the entire search space, but it's not just about blindly trying everything.
So it's more strategic than just randomly guessing.
Exactly. The art lies in cleverly structuring the search and pruning away unnecessary branches like a detective carefully eliminating suspects.
Okay, so it's like a smart brute force using logic and strategy to narrow down the possibilities.
Precisely. Chapter 5 starts with generating subsets, which is like finding all the possible combinations of items in a set.
So if I have a set of ingredients, complete search could help me find every possible recipe.
That's a great analogy. The book shows you how to do this efficiently using bit manipulation and recursion.
It's like flipping switches on and off, where each switch represents an ingredient, and each combination of switches represents a different recipe.
You got it. Then the book moves on to generating permutations, which is finding all the possible orderings of items in a set.
Okay, so permutations are about order, like figuring out all the different seating arrangements for guests at a dinner party.
Exactly. And the book introduces a really powerful technique called backtracking, which is like navigating a maze.
So you explore one path, and if it leads to a dead end, you backtrack and try a different path.
Precisely. Backtracking is especially useful for problems like the classic N queens puzzle, where you need to place N chess queens on a board so that none of them can attack each other.
I love that puzzle. It sounds like a perfect example of how backtracking can help you find a solution by strategically exploring the possibilities.
And the book emphasizes the importance of pruning the search, which means identifying and eliminating branches of the search tree that can't possibly lead to a solution.
It's like recognizing dead ends early on and not wasting time exploring them further.
Right. And then Chapter 5 introduces a really clever technique called meet in the middle, which can sometimes significantly speed up your complete search solutions.
Meet in the middle. Intriguing.
It's like dividing a problem into two halves, solving each half independently, and then ingeniously combining the results.
Oh, I see. Like having two teams working on a puzzle from opposite ends, and they meet in the middle to piece it all together.
Exactly. This technique can be really effective for certain types of problems, especially when the search space is massive.
Okay, so complete search isn't just about brute force. It's about being smart and strategic about how you explore the possibilities.
Absolutely. It's a powerful tool to have in your algorithmic toolbox.
All right, on to Chapter 6, which dives into greedy algorithms.
Greedy algorithms, they have a certain appeal because of their simplicity and speed.
They sound a bit, well, greedy, like they just grab whatever looks best at the moment without really thinking about the long-term consequences.
There's some truth to that. Greedy algorithms make locally optimal choices at each step, hoping that those choices will lead to a globally optimal solution.
So they might miss out on better options later on. Does that actually work?
Well, greedy algorithms don't always guarantee the absolute best solution, but they can be incredibly effective for certain types of problems.
The handbook uses the classic coin problem as an example where You need to use the fewest coins possible to make a specific amount of change, like something we do every day, but to solve it efficiently requires a bit of algorithmic thinking.
It's a great example, and it turns out a greedy approach often works really well for this.
So always picking the largest coin that fits.
Exactly. For many coin systems like the US dollar or the euro, that greedy approach will indeed give you the optimal solution.
But I bet there are cases where it doesn't work.
You're absolutely right. The book provides a counterexample showing how a greedy approach can fail for certain coin systems.
So we need to be careful and make sure our greed doesn't lead us astray.
Exactly. Always analyze and verify your solutions.
Now, scheduling problems, those are something we all face in our daily lives.
Absolutely. Whether it's meetings, projects, or even just figuring out the best order to run errands, scheduling problems are everywhere.
And it turns out greedy algorithms can often help us find good solutions.
That's right. The book presents a problem where you have a set of events with starting and ending times, and you need to find a schedule that includes as many events as possible without any overlaps.
So it's like fitting in as many meetings as possible without double booking yourself.
Exactly. The handbook explores different greedy strategies for this problem, like choosing the shortest events first or choosing the events that end earliest.
That's like having an algorithmic assistant helping you plan your day.
And then there's data compression, another area where greedy algorithms can shine.
Data compression is essential in today's digital world.
Absolutely. And the book focuses on a classic algorithm called Huffman coding, which is a greedy algorithm for creating optimal prefix codes.
Prefix codes. So that's like creating a secret language where no code word is a prefix of another, so you can always decode the message without any ambiguity.
Precisely. Huffman coding assigns shorter codes to more frequent symbols and longer codes to less frequent symbols, which results in really efficient compression.
It's like packing a suitcase, where you fold your most frequently worn clothes neatly to save space.
I love that analogy. It perfectly captures the essence of Huffman coding.
So it seems like greedy algorithms, while not always perfect, can be really powerful for solving a wide range of problems, especially when time and simplicity are key.
Absolutely. They're like the quick and dirty solutions that often get the job done, but sometimes you need a more nuanced approach, and that's where techniques like dynamic programming come into play.
Wow, it feels like we've journeyed through a whole world of algorithms already, from the speed demons of big O notation to the clever strategies of complete search and the efficient shortcuts of greedy algorithms.
It's been quite the adventure, and we've only just scratched the surface. There's so much more to explore in the Competitive Programmer's Handbook.
So what other algorithmic treasures await us? What's next on our agenda?
Well, we've touched upon dynamic programming before, but Chapter 7 really dives deep into this elegant and powerful technique.
Dynamic programming. It's always seemed a bit mysterious to me, like a secret society of elite coders. Is it really that hard to grasp?
I think the mystery comes from how dynamic programming solutions often seem so effortless, almost like they were pulled out of thin air. But the key is understanding a simple but profound principle: optimality.
Optimality. Okay, I'm intrigued. Tell me more.
The principle of optimality states that if you have a globally optimal solution, then any sub-solution within that solution must also be optimal.
So if I found the absolute best route from my house to the beach, then any segment of that route, say, from the coffee shop to the park, must also be the best possible route between those 2 points.
Exactly. Dynamic programming uses this principle to build solutions from the bottom up, storing solutions to smaller subproblems and then using them to solve larger ones.
It's like building a tower brick by brick, making sure each level is strong and stable before adding the next.
A perfect analogy. And the handbook uses the Fibonacci sequence as a classic example. Remember, each number is the sum of the 2 preceding ones: 0, 1, 1, 2, 3, 5, 8, and so on.
Yeah, I remember those from math class. But how does dynamic programming make calculating these numbers faster?
A naive approach would just keep recalculating the same Fibonacci numbers over and over again, but dynamic programming stores the results, so you only compute each one once.
It's like having a cheat sheet where you can look up the answers instead of redoing the work every time.
Exactly. And the handbook goes beyond Fibonacci, exploring more complex dynamic programming problems like the coin problem, the knapsack problem, and the longest increasing subsequence problem. Each one highlights the beauty of breaking down a problem, identifying those optimal substructures, and then systematically building up your solution.
All right, Chapter 8 introduces a concept that sounds more like financial jargon than computer science. Amortized analysis. How does this apply to algorithms?
Well, just like in finance, where you might average the cost of an investment over time. Amortized analysis looks at the average cost of a series of operations, even if some individual operations might be a bit more expensive.
So even if some operations take longer, as long as they happen rarely enough, the overall performance is still good.
Exactly. The book uses the example of a dynamic array that grows as you add elements. Resizing that array can be time-consuming, but it doesn't happen very often. Amortized analysis shows that, on average, the cost of each insertion is still constant time.
It's like saying even if you have to occasionally do a big cleanup of your house, as long as you keep things relatively tidy most of the time, the overall effort isn't too bad.
Chapter 8 also introduces the two-pointers method, which is super useful for problems involving arrays and ranges.
Two-pointers. That sounds deceptively simple.
The power lies in how you move those pointers. Imagine you have two fingers pointing at elements in an array, and you move them strategically based on certain conditions. It's like a synchronized dance, gliding through the array to find the solution.
I like that visual. The handbook shows how this technique can solve problems, like finding pairs that add up to a target, or finding the nearest smaller elements.
And then we have the sliding window minimum problem, which takes this to another level.
Okay, lay it on me. What's the sliding window minimum problem all about?
Imagine a window sliding over an array, and you need to find the smallest value in that window at each step.
It's like scanning a document with a magnifying glass, always focusing on the smallest detail.
Precisely. And this technique has applications in all sorts of fields, from signal processing to image analysis, wherever you need to analyze streams of data.
Chapter 9 delves into range queries, which sound like something you do with a search engine.
In a way, they are. Range queries are all about efficiently finding information within specific parts of an array.
So it's like having a powerful search engine for your data.
Exactly. The handbook starts with static array queries, which work great when your data doesn't change, and you can pre-calculate those answers.
Like having a well-organized library where you can instantly find the book you need.
Perfect analogy. But what if your data is constantly changing?
Yeah, that's a whole different ballgame.
That's where we need dynamic data structures, and the handbook introduces two powerful ones: the binary index tree and the segment tree.
Ah, yes, those were pretty mind-bending at first.
They're definitely clever structures, but the handbook explains them so well, with clear diagrams and examples. It even ties in the idea of bit representation, showing how representing numbers in binary can sometimes lead to super efficient algorithms.
Okay, we're moving into some seriously advanced territory now. My brain is getting a workout.
And we're not done yet. Let's step into the interconnected world of graphs covered in chapters 14 and 15, which explore tree algorithms and spanning trees. Trees are like family trees for data, showing those hierarchical relationships, while spanning trees connect all the nodes of a graph in the most economical way.
It's amazing how graphs can model so many real-world things, from social networks to transportation systems.
The handbook covers essential tree algorithms, including tree traversal, finding the diameter of a tree, and understanding the differences between binary trees and general trees. Then it delves into algorithms for finding those minimum spanning trees, like Kruskal's algorithm and Prim's algorithm.
I remember those. Kruskal's algorithm carefully adds edges one by one, always picking the smallest one that doesn't create a cycle. Prim's algorithm grows the tree one node at a time, making the cheapest choice at each step.
Great descriptions. Then, Chapter 18 takes us even deeper into the world of graph algorithms, exploring fundamental techniques like depth-first search, DFS, and breadth-first search, BFS, two different ways of exploring a maze.
I remember those. DFS is like diving deep into one path until you hit a dead end, while BFS systematically explores every path at a given depth.
Perfect. And the handbook then explores shortest path algorithms, with Dijkstra's algorithm shining for graphs with positive edge weights. But for graphs with negative edge weights, which can represent things like costs or losses, the Bellman-Ford algorithm comes to the rescue.
And let's not forget the Floyd-Warshall algorithm, which solves the all pairs shortest path problem, finding the shortest routes between all pairs of nodes in a graph.
Absolutely essential for things like network routing and mapping applications.
Chapter 21 might seem like a detour into the abstract world of number theory, the study of integers and their properties. But it turns out to be surprisingly relevant to computer science.
Absolutely. I used to think number theory was just about prime numbers, but this chapter opened my eyes to its hidden depths and applications in areas like cryptography.
It's like discovering a secret language that unlocks the mysteries of numbers.
The handbook guides us through essential number theory concepts, from the greatest common divisor, GCD, to modular arithmetic, and those fascinating theorems like Fermat's Little Theorem and the Chinese remainder theorem.
And finally, we reach chapter 26, which focuses on string algorithms. These are essential for processing text, finding patterns, and all those other tasks that involve manipulating sequences of characters, which is basically everything in our digital world.
From the trie-data structure for storing and searching strings efficiently to techniques like string hashing and the Z algorithm for pattern matching, this chapter gives you the tools to work with text effectively.
Wow, what a journey through the world of algorithms. We've covered so much ground, from the basics to some pretty advanced concepts.
The Competitive Programmer's Handbook is an incredible resource for anyone who wants to master the art of problem solving and computational thinking. And remember, it's not just about competitive programming. These algorithms and data structures have applications in countless fields.
Absolutely. It's been like a masterclass in problem solving, and I feel like I've leveled up my coding skills.
Go forth and conquer those coding challenges. Happy coding!